Hi everyone. Welcome back to our lecture series on Introduction to Numerical Methods. In the previous videos, we have discussed about solutions of equations and we discussed various methods to find the solutions of equations, namely bisection method, regular falsi, iteration, and Newton-Raphson method. Now we are moving to the next segment of our lecture, that is interpolation. We will be discussing about interpolation, finite difference, Newton's formulae for interpolation. So in today's lecture we will be discussing what is interpolation and what is the theory behind interpolation and how to define the terms related with interpolation. Mainly interpolation, the process, and the interpolation function, forward differences and backward differences. In the upcoming videos, we'll be discussing about Newton's formulae for interpolation using finite differences. Suppose we have given y equal to x square and asked to find the values of y at various points 0, 1, 2 and 3. It is very easy to find. The question we are going to deal in interpolation is, does the converse hold? That means if you are given there is a function f of x and it takes the values 0, 1, 4 and 9 at 0, 1, 2 and 3 respectively, then what can be the function? Obviously one option is x square, but can we conclude that this is the only function which matches the data set? What about the function g of x, x times x minus 1 times x minus 2 times x minus 3 plus x square? You can observe that this function also attains the values 0, 1, 4 and 9 at 0, 1, 2 and 3 respectively. So now the problem we can state as follows. Find a function y equal to f of x such that for the values of f of x corresponds to x0, x1, etc. xn are y0, y1, etc. yn respectively. The theory behind interpolation is Weierstrass theorem, which states that if f of x is continuous in an interval x0 to xn, then for any epsilon greater than 0, we can find a polynomial Pn of x such that absolute value of f of x minus Pn of x is less than epsilon. In other words, we can approximate any continuous function through a polynomial always. Suppose there is a function y equal to f of x such that x0, y0, x1, y1, xn, yn be values of the function. We need to find the function f of x. As we have discussed earlier, we may not be able to find the unique function f of x, but we will be finding a function phi of x known as interpolating function which agree upon the set of tabulated points with the function y equal to f of x. The process of finding such a function is called interpolation. For interpolation, we require forward differences and backward differences. We will discuss what is forward differences. If y0, y1, yn denote the set of values of y, then we can define first forward differences as delta y0 is equal to y1 minus y0, delta y1 is equal to y2 minus y1, delta yn minus 1 is equal to yn minus yn minus 1. Similarly, we can define second forward differences. Second forward differences are denoted by delta square y0, where delta square y0 is delta y1 minus delta y0. We know that delta y1 is y2 minus y1 and delta y0 is y1 minus y0. So delta square y0 will be y2 minus 2y1 plus y0. Similarly, you can find delta square y1, delta square y2, etc. In a similar way, we can find the third forward difference delta cube yi and the fourth forward difference delta to the power 4 yi as given. Now let us calculate the first forward difference table for a given data. It is given that at x equal to 1, y is 24, at x equal to 3, y is 120, and x equal to 5, y is 336, x equal to 7, y is 120. Let us construct the forward difference table for this data. It is clear that delta y naught is y1 minus y naught, that is 120 minus 24 is 96. Delta y1 is 336 minus 120, which is 216, and delta y2 is 384. So the third column of the table represents delta, that is first forward difference. The second forward difference, delta square, is calculated as delta square y naught is delta y1 minus delta y naught, that is 216 minus 96, which is 120. Delta square y1 is delta y2 minus delta y1, which is 384 minus 216, which is 168. The third forward difference, delta 3 y naught is delta square y1 minus delta square y naught, which is 48. This is how we will calculate the forward difference table. Backward differences are defined as follows. If y0, y1, etc. yn denote the set of values of y, then nabla yn, which is equal to yn minus 1, is the first backward difference. Second backward difference is delta nabla yn minus nabla yn minus 1. Third backward difference is nabla cube yn is equal to nabla square yn minus nabla square yn minus 1. It is a small exercise for you to construct the backward difference table for the previous data. Now try the following problems.